The topic of this video, exponential functions, is focused on growth. So I think before we can really dive into exponential functions and growth and the examples with them, you have to understand the three components. So the first component is the graph. So if you were to look at an XY coordinate, you're going to have a graph that looks something like this, some version of it, if it's some kind of growth, which how I describe that is kind of a slow to quick increase. You're also going to see it curve. That's really important. We are done with lines. So no more lines here at all. You're also going to see it never touch or cross the x-axis right now. And that's really important. Like even if over here, I know I exaggerated it with making there be a huge gap. That's ever so slightly increasing, but just increasing by small amounts. But if you would zoom in on Desmos or whatever calculator you're using, it's not touching that x-axis, and it never will in this case. So that's a big deal. Okay, so we're dealing with a curved graph that's slow to quick increase that doesn't touch or cross the x-axis, right? So that's what our graph looks like. So a table of an exponential function looks something like this. You don't really see a lot of changes in the x values. That's the same. But hopefully what you're noticing and what we did previously is that you notice that the operation that's occurring is multiplication. So this is a really big difference between linear and exponential. So in linear equations, we added. But in exponential, we will always be, no matter what, we are multiplying. Okay? And I think this makes sense because if you think about this, hopefully you recognize that this is multiplying by 4 every time. And so if you think about what's going on here, if we were to represent this, right, this times 4 idea, this would have been like 4 times 4 times 4 times 4, which from our previous standards we know is 4 to the 4th. It introduces an exponent because exponents are repeated multiplication. That is the definition of it. So repeated multiplication, what we're doing here, brings in the exponential aspect. So the table, you're going to see multiplication happening. So the last but not least is the equation, which hopefully all of you saw this in the previous day through exponential 1, that we're dealing with this a times b to the x. So this makes sense that it would be the thing that's being multiplied, right? That repeated multiplication. So, So b is what is multiplied. What is being, I guess, multiplied. Okay, so if you look in your y table or your y column, whatever you're multiplying by, that is the b value, right? So a then is the y-intercept. Or another way to talk about it is the starting value, right? The initial value, okay? So the one thing I like to talk about is there's really a lot of connections between linear functions, y equals mx plus b, and exponential, y equals a times b to the x. So the thing that's with x, which in this case is mx or bx, this is talking about growth or change, right? Both of those were. And granted, the letters are different, but the b and the a here, these are both the y-intercept. And so the one thing I thought was really interesting is if you think about PEMDAS, right? If you think about PEMDAS, wherever we saw multiplication here in the linear function, if we go up one step, we're now multiplying. Wherever we saw addition, if you go up a step, we're now multiplying. So what we did was we took the linear function and we just went up one operation, and that's what creates the different looking equation, the different looking table, and ultimately the different looking graph. Okay, so exponential functions, when you're writing equations, the thing you just need to keep in mind, because that's one of the big things you're going to have to do, is what's the y-intercept or what's the initial amount and what am I multiplying by? okay? And that's all good. So if something is doubling, it's multiplying by 2. If it's tripling, it's multiplying by 3, whatever is happening. But then there's a little extra stint in there, and that's when we start bringing in percentages. So there is something that's called a growth rate versus a growth factor, okay? So the growth factor, that's B, okay, in the equation. I'll make that a lowercase b. That's B in the equation. It's what we were talking about. So if it's doubling, right, if something is doubling, then B is 2. If it's tripling, then B is 3, and we just plug those in, right? Whatever it's multiplying by. But if you're given a percent, that's where things change. Okay, so a growth rate is when you were given like a percentage of growth. Okay, and we have to designate this because that must be turned into a growth factor. Okay, and so the way you do that is you have to kind of think about something. So I'm gonna do this through an example. Okay, so let's say, goodness gracious, let's say we're gaining 15%. Okay, so what you need to understand is that we're getting all of previous back plus the 15%. Okay, so one way to think about this is all the previous back, that's everything that I had before, which is 100%. I'm getting all of that back plus the new percentage, right? So if I added that together, if I did that math, I would have 115%, right? Well, a growth factor cannot be a percent. So we're going to change this into a decimal, which, remember, if you do that, that's dividing by 100, moving your decimal back 2 places. So this becomes 1.15, okay? So now let's just distinguish the difference. So the growth rate was 15%. The growth factor is 1.15. So this is B. So we use the growth rate, this 15%, to lead us to B, but it is not in itself B, okay? So it's really, really important for you to understand like what you're doing with exponential growth. We are adding to 100, okay? Let's look at 2 practice problems. So let's say here you've got a certain bacteria triples itself every hour. If there were 10 bacteria growing in a lab, how many would there be after 5 hours? So this 10 bacteria growing, this is my initial amount. It's how many I'm starting with, right? So this is A, okay? And then it says that it is tripling every hour, right? So this is going to be B because it's talking about growth, okay? So when I go to, before I can even get the 5 hours, I'm going to go ahead and write the equation. So y equals A, which is 10 times 3 to the power of x, okay? So because this 3 is what I'm multiplying by. So now if I want to know 5 hours, I take that 5 and I plug it in for x. So 10 times 3 to the 5th. And when you plug that into your calculator, you get 2,430 bacteria. All right. So this is just an example of I was given a growth rate, or a growth factor, But let's take a look at an example where I was given a growth rate. So if I look at this bottom question here, a 1970 comic book has appreciated 10% per year and originally sold for 35 cents. What will it be worth in 2020? So you can see this 10% appreciated, first of all, means a growth, okay? So this 10% is not a growth factor, okay? So we need to change it into one. So the thing we have to think about is we have the 35 cents, the original amount, right, plus an additional 10, and that happens every single year. So we have the 100% from the beginning, plus we have the 10% now, and that equals 110%, which as a decimal is 1.01, or 1.10, excuse me. So this is B. And the original amount is 35 cents. So our equation is going to be 0.35 times 1.0 or 1.10 to the power of x. And then we think about, well, what about 2020? Well, we just have to calculate the distance between 1970 and 2020, which is 50 years. So 0.35 times 1.10 to the 50th power, and that would tell us how much this comic book is worth. And once you plug that in, you get $41.09. Okay? So notice again, when you have that percent, you need to go ahead and change it through. So at this point, I want you to go through and start looking through some more examples and pinpointing, do you have the rate, do you have the factor, what's the y-intercept, what's the initial amount, and putting those functions together.